All right, welcome back. In this lecture, I'm going to cover 6.3 ionic bonding and ionic compounds, and basically talk about the chemical formula in ionic compounds, go through some key vocab terms, and then go through write-in Lewis structures for polyatomic ions for your assignment today. So an ionic compound is a compound that has both positive and negative charges, and they combine in a way so that the positive charge and the negative charges are equal. So take a look at my table here of cations versus anions. If I have calcium chloride, calcium bonded to chlorine, calcium has a +2 charge and chlorine has a -1 charge. And notice that the charges are not balanced. So, I need 2 chlorines for an overall -2 charge to cancel out the calcium +2 charge. And then here's my compound, calcium chloride, 2 of them. So for every +2 calcium ion, I have 2 -1 chloride ions. Here I have barium and oxygen. Barium's in group 2, +2. Oxygen with a -2 charge. The charges cancel each other out, so they are equal. So I just write BaO, I got 1 of each. Over here we have potassium bonded to sulfur. Potassium with a +1, sulfur with a -2. Notice that I need 2 potassiums to cancel out the -2 charge for sulfur. So 2 of these guys means +2 overall, and it balances or cancels the -2. And you can go on and on. Oh, let's talk about this last one. Chromium oxide. Chromium has a +3 charge, and oxygen has a -2 charge. So like over here, we could just like double it or triple it, and we're fine. But down here, you have to think of a common number that they both go into. So, 3 and 2, the least common number that they go into is 6. So how many times do I have to multiply a 3 to get to 6? 2 of them, hence the 2 down here, for an overall +6 charge. And then oxygen with a -2, well, how many times do I have to multiply a -2 to get to a -6? That'd be 3. So O3, so Cr2O3. Here's a list of some common ions that are positive on this side and negative on the other, and then we'll talk about polyatomic because you can see that there are 2 elements here with an overall charge. So properties of ionic compounds, number 1, they exist as a crystalline solid, basically a 3D network of ions attracted to each other. And this network of ions, it's going to be positive and negative to equal out each other. So when they are all bonded together, this is neutral. Okay, this is also not a molecular compound. These are not independent neutral units that you can isolate and examine. In their crystalline solid structure, the ions minimize their potential energy by combining in a nice little arrangement, which we call a crystal lattice structure. And just keep in mind that sizes and charges of ions do vary. So here I have calcium bonded to fluorine, and you can see that the calcium ion is smaller than fluorine. I put down here calcium fluoride versus NaCl. So this is calcium fluoride, this is NaCl. And so you can see that for every 1 calcium, there are 2 fluorines, and here we have a nice 1-to-1 ratio. Now, in this crystal lattice structure, there are both repulsive and attractive forces. They're still there, okay, but just keep in mind that they are balancing or equaling out. Also, the chemical formula of ionic compounds is the simplest ratio of ions, not molecules. Okay, we're looking at ions here. So we call this the formula unit. So a collection of atoms from which an ionic compound's formula can be established. It's the lowest whole number ratio of ions in that ionic compound. Okay, the latest energy is the energy that is released when the crystalline compound is formed. This is not bond energy, okay? It's kind of similar, but it's not. So if I take a look at sodium chloride with a +1, -1 charge, and then I take a look at sodium bromine, same thing here, but then I jump down to calcium fluoride where it's a 2-to-1 ratio and a 2-to-2 ratio, what happens to your latest energy? Okay, it increases, except for this little thing right here, but the higher your charges, it tends to increase, and that has everything to do with those electron negativities and their ionization energies and their trends associated with that. Okay, so how do we form a compound? Okay, well, with ionic compounds, we are transferring electrons, and when we transfer electrons, the protons and the electrons are no longer balanced, and as a result, we end up with charges or ions. And then, depending on those charges, if they are balanced and equal, then attraction will take place. So it usually occurs between a metal and a nonmetal. So in my classic example of sodium chloride, sodium is my metal and chloride is my nonmetal, a halogen. And sodium has 1 valence electron in its outermost energy shell. And chlorine has 7 in its outermost energy shell, and it just needs 1 more, so sodium's going to transfer that electron. Now sodium started out with 11 protons and 11 electrons, and now it's lost that electron. So now it has 11 protons and 10 electrons. So it's got an overall +1 charge. The protons and the electrons no longer are balanced. Now chlorine, which is element 17, has 17 protons because it's still chlorine. Now it has 17 electrons, and so now it has a -1 charge. So you can see that they are transferring that electron over, and now both are happy. If we take a look at their electron negativity, sodium has an outer valence shell, like 8, okay, and chlorine over here also now has 8. So now they have achieved noble gas configuration. So when we compare ionic and molecular compounds to each other, just know that the force that holds ionic compounds together is a very, very strong electrostatic attraction. And what I mean by strong, I mean very high melting points. Ionic compounds are hard, but they are brittle. You can take halite, which is just like rock salts, like big clumps of salt, and when you break it, it's very easy to break and break down. But every time you break it, it follows the crystalline structure of that salt. Not electrical conductors as solids, but when they are in a molten state or even in a liquid state, then they will conduct electricity. Sorry. Okay, so the forces of attraction between molecules of a covalent compound are much weaker. They have very low melting points. So like sugar, it doesn't take much to melt sugar, and then you end up with this kind of dark, gooey mess in your kitchen. But if you take a look at this table here of ionic compounds, the top 3 are ionic, take a look at those melting points and the boiling points and compare them to covalent compounds where they have much lower melting and boiling points. Okay, so now moving on to the big thing here with polyatomic ions and drawing of Lewis structures of these guys. So a polyatomic ion, if we break down the word poly, means many, and atomic means atoms, and many atoms that have charges, and they are grouped together, and they are held by covalent bonds, but they have a charge, okay? It's either going to be positive or negative. So they're covalently bonded together, but they have a charge. So as a result, it has both molecular and ionic characteristics. We're sharing electrons, but the charge is due to an excess or shortage of electrons. You're like, what? And I'll explain that in a bit. So you have to count the valence electrons correctly, and then put the Lewis structure in brackets with the noted charge to show that this is a polyatomic ion and it doesn't really fit the bill. So here is a table, and your book also has a table of polyatomic ions, so you'll need to reference that. But these are your ions with a -1 charge, and then we go down to ions with a -2 and -3 and a +1. Now this table is not complete. This doesn't have all of them. Okay, so let's just do some examples here. Show you what's going on. So notice that I have my spinning wheel of death. Okay, my ammonium ion. Okay, so nitrogen has 5 valence electrons, and then I have 4 hydrogens at 1 apiece for 4, and I have, as a result, 9 valence electrons. But because it has a +1 charge, that means it has lost an electron. So 9 minus 1 is 8. So then you're actually dealing with 8 valence electrons. So you put your nitrogen in the center, and this is where it also gets a little bit screwy, because, I've been saying, hey, nitrogen is in group 15 and it, wants to form 3 bonds. Well, here you can see that rule is not being honored, okay? Hydrogen still holds 1 bond, but some other elements may go one more past than what you are used to seeing. So you draw sodium in the center, and you got your hydrogens branched off of it, and then you count your 8 valence electrons, 2, 4, 6, 8, and then you put it in brackets, and you showed that plus 1 because, it's supposed to have 9, but it has lost an electron to something, or somewhere. Same thing with nitrate. So nitrogen has 5, and then we have 3 oxygens at 3 apiece for 18. So then you take 18 plus 5, right, and you get 23 valence electrons. But because it has a minus 1, now you're going to add, because it's, it's more negative. So you're going to add 1. And when you add 1, now you have 24 valence electrons. Now you're still going to put sodium. Why do I keep saying sodium? You're still going to put nitrogen in the center because it has the lower electronegativity value. And then you're going to branch your oxygens out. So let me just draw that for you here. Because you'll see that there's a double bond. Boop, boop, boop. So remember with our rules, I said fill everything, octets, and see if it works. All right, so I had to have 24 valence electrons. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I am 1 past. So that means there has to be a double bond somewhere. And you can choose this double bond between any of the oxygens. Okay, so they chose to do it between the nitrogen and the oxygen. It's got to be with the nitrogen for sure. So then there's your double bond. You erase the lone pairs. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 20. Well, I really miscounted. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And then do I have an octet? Yes. Does this have an octet? Yes. Does this have an octet? Yes. Does nitrogen have an octet? Yes. Okay. Same thing with the sulfite ion here. Sulfur is in group 16, so it has 6 valence electrons. So I have 6 plus 4 oxygens at 6 apiece for 24. Yep, I'm just doing math in my head. It's really early in the morning here. So that's 30. And then this minus 2 actually means plus 2. Okay, so that minus 2 charge means we're going to add 2 more electrons for 32 valence electrons. Okay, so you put sulfur in the middle and you branch it all off, and then you check to see if you got 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Then you put it in brackets and put the charge. So here we are given hydroxide. Okay, so oxygen has 6 and hydrogen has 1. And this minus 1, you're going to do the opposite. You're going to add 1 for a total of 8 valence electrons. So I have my oxygen bonded to my hydrogen. Then I'm going to go ahead and fill in my lone pairs of my oxygen because hydrogen's happy. 2, 4, 6, 8. You're not done. It has a charge. You have to put it in brackets, and it's a minus 1 charge. PO4 minus 3. Phosphorus is in group 15 and it has 5 valence electrons. So I have 5 plus 4 oxygens at 6 apiece. Okay, that's going to give you 29. And then this minus 3 means you need to add 3. So now you have 32 valence electrons. So phosphorus is going to be in your center, and then you're going to branch your oxygens around. And then you're going to fulfill the octets, and you're going to hope that it equals 32. And if not, then that means that you probably have to do a double bond or a triple bond somewhere, right? Okay, let's see if phosphorus has an octet. 2, 4, 6, 8. Yep. This is oxygen, have an octet. 2, 4, 6, 8. Yep. This one, 2, 4, 6, 8. Yep. This one, 2, 4, 6, 8. Yep. And this one, 2, 4, 6, 8. Yep. Okay, now do I have 32 valence electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And then because we added some electrons, we have to put the whole thing in a bracket and denote the charge, -3. So that is how you do polyatomic. Basically, you're counting your valence electrons, and you take a look at the charge. If it's minus, that means you will add. Okay, I should have done one with a positive, like one down here. If it's positive, you will subtract. Okay, so if that's positive charge, you will subtract. I think on the homework assignment, I give you the chemical formula. I know further down the line, you'll be given the name, and you're like, what chemical what does that look like? But I'm pretty sure for the homework assignment, I give you the formula unit, and you just have to draw the structure.